Hey legends, welcome back to another episode of McGrathematics. Sorry these uploads haven't been super regular recently. Term 2 is really cooking me, but I promise I'll get all of my Extension 2 videos done before the HSC exam. Fingers crossed. Alright, starting off with a flashback from last year's HSC exam, we've got expressing this fraction as a sum of partial fractions over r. So for 3 marks, split this into partial fractions. Okay, so to answer this question, we need to know how to set up our partial fractions like this. We're splitting it apart with x minus 2 with a constant on the top, and then the x squared plus x plus 1 fraction. Because the bottom of the fraction is a quadratic, the top needs to be a generic linear function, so something times x plus a constant. Okay, so general rule for partial fractions is that the top of your fraction should be 1 degree less than your bottom. Okay, if we make both sides look similar in terms of denominators, we end up by comparing the numerators and having 3x squared minus 5 equals a times this denominator plus bx plus c times this denominator. If that jump was too quick for you, I do have a video on partial fractions that you can look through for a more detailed solution on this kind of stuff. Okay, now my method for solving these is I sub in some convenient values to solve for a, b, and c. So first thing I notice is that if I sub in x equals 2, this bracket is going to turn into 0, and it's going to give me a solution for a. So if I sub in x equals 2, on the left we're going to end up with 7, and on the right we're going to end up with 0 on the end and a 7a here. So that very quickly gets us the value of a being equal to 1. Okay, next convenient value is we can substitute in x equals 0 to get rid of the b, and that's going to allow us to solve for c now that we know what a is. So subbing in 0 now, on the left we're going to end up with negative 5. We'll have 1 times 0 plus 1 here, and then we'll have c times minus 2. That gets us a quick little equation to solve for c, and we end up with c equal to positive 3. Now we know what a and c are, we can sub them into our expression here. So we've got 1 here, and we've got 3 here. Now because there's only one unknown remaining, we can sub in whatever number we want. I'm going to go with x equals 1. On the left hand side we end up with minus 2. We're going to get 3 here, and then we're going to get b plus 3 times minus 1. So again, quick little equation to solve. If we solve this for b, we end up with b equal to 2. And now we have our 3 constants. We just write them into our answer, and there is our partial fractions breakdown for 3 marks. All right, cool. On to today's lesson. We are looking at integration by parts. This is our second last lesson in integration for this channel. This is essentially doing the product rule for differentiation in reverse. Really useful for integrating a lot of things such as products and some weird stuff like logs and inverse trig. So here is the by parts formula. It is going to be on your reference sheet, but once you've done a few examples, you will memorize this pretty quick. It's not too challenging. I'm going to show you an example of how we use this formula, and then I'll show you how this formula works by rearranging the product rule. So a typical kind of question we could use integration by parts for would be a product such as x times sine x. Now the key to these questions is you need to identify half of your product as something that you want to differentiate and the other half that you want to integrate. And again, once you've done a few examples, picking which is which will become easier. It does seem a bit tough at first. What we're going to do is we're going to set, here's our by parts formula, which we'll use in a sec. We're going to set x as the thing we're going to differentiate, because that's going to turn into 1, which is going to make our answer nice and simple, okay? Which means the other half, the sine x, is the part that we need to integrate. So that's our u, and that's our v prime. So we're going to go to u dash by differentiating, so we get u dash as 1. We're going to integrate v prime to end up with v, which is negative cos x. Don't worry about the constant, we'll put that in at the end of the example. Okay, now we substitute this information into our by parts formula. So this is the left-hand side. This is our u v dash. So on the right, we're going to have uv, which is the 2 letters with our dashes. And then we take away the integral of the bottom row, u dash v. So I recommend setting your question out like this, so you know that you've just got the uv at the front, and then you integrate the bottom row. It makes it super straightforward, and you're not going to muck yourself up. So here's our formula. We've got u here being x. We've got our v, which is negative cos x. Now we take away the integral of u dash v. Now if you've done this right, what you're left with should be an integral that's relatively easy to handle. We can put the negative out the front to end up with plus integral cos x. Of course we know the integral of cos x is just sine x, so we integrate to sine x with a constant with the minus x cos x out the front, and there is the integral of x sine x. Okay, so some questions, if you use by parts, you can get to your answer very quickly if the remaining integral is nice and friendly. Okay, so that's how we use it. Here is why the by parts formula works. We're going to start with the good old-fashioned product rule from the advanced course. So we have the derivative of a product. We differentiate each part separately and then sum together the result. I'm just going to rearrange this formula by subtracting the u dash v across to the left and then swapping sides. So moving the u dash v across. Now we have this result here. And what we'll do is we're going to integrate everything. So we're going to integrate throughout the expression. We get the integral of uv dash, and then in the middle we have the integral of the derivative. And because they are essentially inverse operations, these guys cancel out and leave you with your original function, which was uv. Okay, and that is where we get the by parts formula from. Literally just a product rule moved around and then integrated. All right, cool, that's why it works. Let's look at a few more examples of how we can use by parts to integrate some cool stuff, such as the integral of inverse sine. Okay, so if you want to integrate inverse sine, inverse cos, inverse tan, or even log x, you need to think of that as a product and use the by parts formula. Okay, even though this doesn't really look like a product, what it really is sine inverse x times 1. Okay, so what we're going to do is we're going to look up our formula if we haven't memorized it yet. We're going to set sine x as the half of the product that we're going to differentiate. So that's going to be our u. The other half, which is the invisible 1, that's what we are going to integrate. That's going to be our v dash. Okay, there's our setup. That's usually the hardest part, is picking which to differentiate, which to integrate. If you do that correctly, the rest should flow relatively nicely. So differentiating sine inverse from the extension 1 course looks like this. Hopefully you are familiar with that. And integrating 1 turns into x. All right, subbing into our by parts formula. So we're going to have uv on the left here. So we've got sine inverse x just out the front. Take away the integral of the bottom row. So 1 over root 1 minus x squared times x. Okay, now all we need to do is figure out how to integrate x over the square root of 1 minus x squared. Now what I'm noticing is that the derivative of the function inside the square root is negative 2x. So if I can make the top of this fraction into a negative 2x, I'll have a function multiplied by its derivative dx. So it'll be in good position for a cheeky little substitution. So we're going to substitute u equal to 1 minus x squared, which means that du is equal to minus 2x dx. That's just differentiating both sides. Now subbing in, we're going to change the, no we're not, we're going to put a negative 2 on the top and keeping the balance by putting a negative half out the front. So I haven't changed the value of the integral. Now inside my square root, I have my substitution, 1 minus x squared. And on the top, I have negative 2x dx, which is a substitution for du. So it works out quite nicely. Now we just need to integrate 1 over the square root of u. We can do this by writing this as u to the power of negative a half, and then applying good old-fashioned integration, adding 1 to the power, and then dividing by the new power of a half. Now these halves fortunately are going to cancel out, and u to the power of a half is the square root of u, which is the square root of 1 minus x squared. So we end up with x sine inverse x plus the square root of 1 minus x squared plus c. And there's our final answer. Don't forget your plus c, or it's 10 push-ups. All right, outstanding. Let's move on to the next one. Now we're looking at an example involving limits and how that changes our by parts formula. So for limits questions, all you need to do is remember that the uv, the bit in the middle of the formula, is something that's already been integrated. So you need to apply your limits to uv as if you've just integrated them. Apart from that, everything else remains the same. Same limits in the question as in your resulting integral. All right, so our product is x log x. We need to identify which half of this we want to differentiate and which half we want to integrate. Now, integrating log x is very hard, so that's going to be the thing that we're going to differentiate, whereas x is pretty easy to integrate, so we're going to integrate x and differentiate log x. So I'm setting u as log x, I'm setting v dash as x, differentiating log x to 1 over x, and then integrating x to x squared over 2. Okay, there's our setup all done. Let's sub into our by parts formula just here. So we have uv in the middle, so we have log x times x squared on 2, and don't forget, because we had limits, we need to apply those limits to our uv in the middle. Take away the integral from 1 to 2 of u dash v, which again is just our bottom row. So 1 over x multiplied by x squared over 2. Okay, subbing in our limits. So when we sub in 2, we're going to end up with 4 over 2. So we're going to have 2 log 2. And then fortunately, when we sub in 1, we know that log of 1 is equal to 0. So subbing in 1 just gets us 0, and we don't need to worry about it. We just sub in 2. So we get 2 log 2, as I said. We can put the half out the front of the integral, and then x squared divided by x is just x. So our resulting integral is very easy to handle. Just some good old-fashioned integration now by raising the power to 2, dividing by 2, applying our limits of 2 and 1, and we're going to get to our answer pretty easily. So there's 2 subbed in, and there's 1 subbed in, getting us a final answer of 2 log 2, take away 3/4. Okay, so limits don't really make that much scary. You don't need your plus c. And yeah, just remember to put your limits into your UV, and you're going to be right as rain. Okay, on to example 4. Getting a bit spicier now. We've got the integral of x squared e to the x. All right, so thinking about which part we want to differentiate. We could differentiate either of these because it's both pretty easy. We could also integrate both of them because they're just x squared and e to the x. What we want to think about is what is going to reduce the difficulty or the power of our resulting integral. For that reason, I'm going to set x squared as the thing we're going to differentiate to bring the power down to 2x, and we're going to just integrate e to the x. Okay, so we're going to reduce the power of the integral, making our answer easier to handle. So setting our u as x squared, which means we're setting our v prime as e to the x. Derivative of u is, of course, 2x, and the integral of e to the x is still e to the x. Now, subbing into our by parts formula, we have uv at the start, so we have x squared e to the x. Take away the integral of the bottom row, 2x times e to the x dx. Okay, now the extra spice to this question is that now we need to integrate 2 times x times e to the x. So we are once again integrating a product, and so to handle x e to the x, we need to once again use by parts. So this is a question that relies on 2 applications of the by parts formula. So let's go again. Let's set the x as the thing we're going to differentiate into a 1. And once again, the e to the x is the thing we're going to integrate, which keeps it as e to the x. We'll put the 2 out the front of the integral, and then we have our by parts formula again inside these brackets. We have uv at the front, so x e to the x. Take away the integral of the bottom row, which is u dash v, which fortunately now is just e to the x. And so finally we have an integral that we can actually evaluate and get our final answer. So expanding that out, we get minus 2x e to the x. We're going to get positive 2, and then the integral of e to the x is of course still e to the x. Don't forget your plus c, and there is our final answer for the integral of x squared e to the x. All right, so sometimes one by parts is just not enough. Let's look at another example where we need multiple applications of the by parts formula. Here we have the integral of e to the x cos x dx. Now this example is a bit trickier because if we're sort of thinking forward, if we're differentiating e to the x, it's not going to change. And if we're differentiating cos x, it's just going to go between cos and sine forever. So we're not going to get anywhere unless we approach this in a really clever way. So what we're going to do is we're going to set the cos as the thing we're going to differentiate. So we get u prime is of course negative sine x. Now the e to the x we are once again going to integrate, and so it remains the same as e to the x. Okay, now using our by parts formula, and trick to this question is we need to label our starting integral as a pronumeral. I'm going to call it I for integral. Okay, you can call it whatever you want. Okay, so I is equal to, using our by parts formula, we've got uv at the front, take away the integral of u prime v, which is our bottom row. Now putting the negative out the front, now we have the integral of e to the x sine x. So it doesn't really feel like we've gotten anywhere, but just stay with me on this, it's going to be poetry really soon. We're going to use the by parts formula on this once more. We're going to differentiate sine x, and we're going to keep integrating e to the x. So we're going to set u as sine x, so u prime is cos x. We're going to set e to the x as v prime, so we're going to integrate that to e to the x. Now we just apply integration by parts for another occasion, so we're just going to have some brackets in here. So our integral on the end turns into uv at the front, take away the integral of u dash v. Okay, so it kind of looks like we just got back to the start because now we need to integrate e to the x cos x until you realize that, hang on, this is the same thing as we started with. This is equal to I. So we can actually rewrite this integral here as just I. Now, why this is good is because we can group it with the I on the left-hand side, so we can add I to both sides. So on the left, we get 2I, and now we just divide both sides by 2, and now we have an expression for our integral. There is our answer. It's a half of e to the x cos x plus e to the x sin x. Of course, don't forget, we just did some integration and it was an indefinite integral, so of course we need a plus c on the end. So don't forget that. Okay, cool. So it kind of feels like we integrated without actually integrating, although we did integrate twice. But yeah, it just kind of feels like magic, but sometimes that's just maths, baby. Okay, so here's some advice from the Oracle Steve Howard on if you're struggling with deciding on which you should integrate and what you should differentiate. His mnemonic is detail. So basically, if it's exponential or trigonometric, that's the best thing you want to set for the thing that you want to integrate. So this is kind of like a list of what you look for to integrate. Start with exponentials, then trigonometrics, then algebra. And then the ones you want to leave for last are inverse trig and logs because they are very hard to integrate. So they're better to be the half of the function that you differentiate. Okay. So top of the list is good for integration. The bottom of the list is better for the differentiation, if that makes sense, hopefully. Okay, a couple of quick examples on questions that kind of look like you should be using by parts, but actually if you think about them cleverly, there is a bit of a shortcut. And the shortcut for questions like these, when you spot that you're working with symmetric limits, so negative and positive of the same number, it's good to think about odd and even functions because these are pretty common multiple choice questions. So odd and even functions kind of work, in my mind, similar to how positive and negative numbers work. If you multiply two even functions together, the result will be an even function. If you multiply two odd functions together, the result is also even. If you're multiplying difference, so even and odd or odd and even, the result is an odd function. So again, this kind of works in my mind like positive and negative numbers. If they're the same, you end up with positive, aka even. If they're different, you end up with odd, aka negative. Now, the good thing about odd functions is that when you integrate odd functions between symmetric limits, if you can picture an odd function in your head right now, which you should be able to from the advanced course, the areas above and below the x-axis cancel out and you get an answer of 0. So integrating an odd function between symmetric limits is always going to be equal to 0. So right here, what have we got? We've got x squared, which if you picture a parabola, that's an even function. X squared is even. Sine x is an odd function. Okay, so sine and tan are odd functions. Cos is an even function. So in this left one, we have an even function times an odd function, which means our result is an odd function. So when we integrate between a negative and positive value, the areas cancel out and the answer is just 0. Over on the right, we have cos, which is an even function, and so cos squared is also even. We have an odd power of sine, which means so sine is odd, sine squared is even, and then sine cubed is also odd. So we have an odd function multiplied by an even function, so we have an odd result. Between symmetric limits, once again, the areas are going to cancel out and leave you with 0. So for multiple choice questions, sometimes think about odd and even functions because they can save you a fair bit of work. Okay, and finishing off with a challenge question from the 2016 HSC. This is a very challenging integral, one of the hardest integrals I've seen in recent HSC exams. If you love a challenge, of course, pause the video, try and have a crack, otherwise work through it with me. If you want a hint to start off with, a good place to start is to substitute u equal to log x, okay? Because we've got a log x on the top and on the bottom. Okay, so diving in, we're going to do the derivative of u with respect to x is 1 over x, and that rearranges to give us dx is equal to du times x. Okay, that's going to be our substitution for dx. So subbing all those values in, we have a u on the top, we have a 1 plus u squared on the bottom. Our dx is now x du. So the issue with this is that we still have an x in our answer and we want it to be only involving u. So we go back to our substitution and say, well, if u is equal to log base e of x, if we rearrange this to make x the subject, we end up with x equal to e to the u, using our definition of a logarithm. Okay, e to the u equal to x. So substituting this into our integral, we're going to change the x to an e to the u. And now we've got to figure out how to integrate this, which is very, very challenging. We're going to use an application of splitting the numerator from one of my very earlier videos. What we need to do is we need to have a 1 plus u in the top of this fraction. So I'm going to put a 1 plus u up there. Which means to the top of my fraction, I have added in 1 times e to the power of u. So to keep the balance and make sure I haven't changed the question, I need to subtract 1 lot of e to the u. Okay, so this right here is me adding to the top and taking away to the top 1 times e to the u. Now we can split this apart, and we have the 1 plus u's are going to cancel out on the left-hand fraction. On the right, we have e to the u over 1 plus u squared. And now we've got to figure out how to integrate this, which, believe it or not, can be done using the magic of integration by parts, hence why it is at the end of my integration by parts video. So what we're going to do is we're going to set the top, the e to the u, that's what we're going to differentiate, and we're going to integrate 1 over 1 plus u squared, which we're going to write as 1 plus u to the power of minus 2. Okay, it's a bit messy, but it is doable. So we're going to differentiate e to the u to be e to the u. We're going to integrate this to become 1 plus u to the power of negative 1 divided by negative 1. So we've got a negative 1 out the front. Okay, let's substitute these expressions into our integration by parts formula for the right-hand integral. We're going to leave the left-hand one alone for now, and you'll see why. It's a bit of poetry towards the end of the example, but yeah, just leave this one alone for now. Integration by parts for this one. That's cool. Okay, so we have the left-hand integral just there, just chilling. Now we have take away. We've got uv at the front. That right there is my uv. Now take away the integral of u prime v right there. Okay, so it looks like a massive mess. We can put the negative at the front there, and then there's a lot of negatives flying around, so be careful with your negatives for this question. Simplifying a bit, we get positive e to the u over 1 plus u. That's what our front term simplifies to. Now we've got negative, 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 so we have a negative here. We have e to the u over 1 plus u as an integral. Okay, that's why this was a good idea to leave the integral of e to the u 1 plus u at the front, because now we have a takeaway integral of e to the u over 1 plus u. So these guys just cancel out, and then there's no more integration. We're just left with e to the u over 1 plus u. Of course, we've just done some integration, so I should probably chuck a plus c in there just for good measure. And now we just back substitute the fact that u at the very start was log x, and e to the u was our expression right here for x. So there is our final answer, which gets us 3 marks in a band 6 integration question. Yep, pretty gnarly, but that's extension 2 for you. Sometimes it's a bit of chaos, but you know, we love the grind, don't we? That's what we're here for. All right, cool. Hopefully that was of some use to you, and thank you for watching if you made it that far. Some recommended exercises from the Cambridge textbook, or of course, Howard Mathematics has some great free exercises in his textbook. Okay, cool. Thanks for watching. See you again in the next video in 1 to 4 weeks. All right, catch you guys.